Hello everyone, this is Daniel Antoniak. Together with my colleague Ben Flanagan, we will talk about how changes introduced by AASHTO LRFD 10th edition have been implemented in BrDR. A few words about myself. My PhD is in structural engineering. I also have a master's degree in software engineering, and I've been developing structural engineering software for more than 20 years. Last 5 of which have been at ProMals on the AASHTOWare bridge team. I'll just stop my video and I will continue with the presentation. We have 4 topics that we'll cover today. The first 2 topics are on concrete. I'll cover those. And the last 2 topics are on steel. Ben will present those. The ones that I'll be presenting will be on concrete deflections and development length. So this is the first topic, concrete deflections. And this is the time for the first poll question. So whenever it comes up, please answer the question, and I'll continue with the presentation on concrete deflections. So the biggest change introduced by LRFD 10th edition for concrete deflections is that the article that covers those has been split into two parts, A and B. The first part is on instantaneous deflection. Now the second part is on time-dependent deflections. There's also a name change. They used to be called long-term. Now they're called time-dependent. And in both of these changes, the formulas have changed. I'm showing the formulas here.
I'm sorry, Daniel. Do you mind just speaking a little louder? We got a message. It's a little hard to hear.
Yes, I'll try to speak louder then. I'll go back. On the left-hand side, we see the deflections based on the LRFD 9th edition. On the right-hand side, it's for the 10th edition. The formulas are not that much different. They're both based on the ratio of cracking moment to the service 1 moment. And then there is also a change in how time-dependent deflections are calculated. There is this lambda d factor now that comes from the ACI 318 code. Now in LRF in BrDR we did not have any of those implemented. So we didn't have these formulas on the left-hand side. We did not have the formulas on the right-hand side. We were just calculating up to BrDR 7.5 and up to LRFD 9th edition. Everything was based on gross moment of inertia. It's only now in BrDR version 7.6 and LRFD 10th where we can calculate instantaneous deflections like this year's and this year's. We can calculate them based on the effective moment of inertia. We also did not have the time-dependent deflections for RC. We did not have them for PS either, not at least in BRD. We did have them for prestressed design tool, PSDT, but they were calculated based on PCI multipliers, not the formulas from LRFD. So we still don't have. Yes.
So sorry, Daniel. We missed our first poll question. So once you are finished with this slide, we'll just go back and we'll launch the first poll question for people to answer.
So I should wait then?
You can finish this slide and then I'll watch it.
Okay. Now, so we still don't have the time-dependent deflections in BrDR 4PS, and it's just because the factor that AASHTO gives us, LRFD 10th edition gives us, just does not apply to PS. We still can calculate the long-term deflection in prestressed design tool, but again, it's just based on different factor coming from PCI. This flowchart shows the workflow on how instantaneous deflections are calculated. The highlighted parts is where we do analysis, the finite element analysis. So first we do the finite element analysis based on IG, that's the gross moment of inertia. And then we do all the spec checking based on forces calculated using that gross moment of inertia, except this article which checks the instantaneous deflections. And that's because to get to here to the instantaneous deflections, we have to calculate this effective moment of inertia, which we do based on the results from the first analysis. Then along the way, we check if it's a pre-stress member, and that's just because for pre-stress members, if the tensile stresses are low enough, then we don't really have to do the second analysis based on I effective. We can just go with the deflections calculated based on I gross. So it's this branch here. But if it's a reinforced concrete member or PS member with large enough tensile stresses, then we run this second analysis using I effective, and then we check that article that we skipped here using the deflections coming from I effective.
And I'm going to just pause right here. We're getting a few comments about the audio. So I'm going to launch our first poll question, and we will go back and make sure the audio is working for everyone to hear a bit better. So I'm going to launch this first question here. All right. And the chat, I have a message here that the chat is disabled. It should be working. I have received a few messages from folks via the chat, but please let me know if you're not able to use it. Questions can be asked in the Q&A portion of the chat here. Awesome, thank you. And we've got some ProMouse folks answering questions live in the questions portion here. And I think, I'm sorry, I might have been mistaken. The chat is going to be disabled, but any questions can be asked either directly to the group, or they can be directed individually to the panelists and the hosts. So please let us know. And I think that, let's see. We will also share these slides and a recording to the webinar after this is finished. So we have a few more people answering questions. About 85% of you participated. Okay, great. So we have 100% answered. It looks like 75% of our attendees, it's just you all attending at your location, but 4% of you have 10 or more, so that's very impressive. Please let us know if any of your 10 have any questions. I'm going to end this poll. And Daniel, I think you can continue. If you don't mind, just maybe speaking a little slower and as loudly as you can, just so that the attendees can hear. And I will answer this question that just came in. We will let the presentation run through completely, and all questions will be answered at the end. Just want to make sure that everyone can hear the presentation before we get too deep into it. And go ahead, Daniel. Thank you.
Yes, I'll try louder, slower. Not sure. We have a lot of ground to cover, so
that's better.
Why,
that's great.
yes,
thank you.
Me speaking quickly and with my accent, yes, I can understand. But yeah, the audio may not be going through correctly. So let me continue for the time-dependent deflections. What I highlighted here, excuse me, is where we calculate the instantaneous deflections that are actually used for time-dependent deflections. These are the deflections due to sustained loads, and they are then combined using service worn load combinations, load combination factors. So we calculate it here, and before we get to here, we calculate these lambda d factors. Then we multiply these deflections by the lambda d factor calculated here. This gives us the additional time-dependent deflections, and then the total is just the sum of the instantaneous plus the time-dependent. This gives us the total. Now I'll move on to show where to find all of these deflections. We have so many different types. It can be, just to clarify, because it can be confusing, which are which. The ones that we use to calculate the actions, like the moment and shear and axial. So the deflections that accompany these results, these are the deflections from the first analysis, like I'm showing here. There is the first analysis, finite element analysis, and that one uses the IG, which is the gross moment of inertia. So whenever we see them together, these are the deflections based on IG. And they will show up under tabular results here and the results graph, in the results graph. Now the deflections based on I effective will be listed under engine outputs. We create specific models to come up with these deflections. So they have this deflection word that is part of the name. So these values that you see here, these deflections and the time-dependent deflections that are, again, based on instantaneous deflections, these are calculated from the second finite element analysis. It says here, starting instantaneous deflections, FEA, using effective moment of inertia. So these are these deflections under engine output. Now, these models that I'm showing here, they use effective moment of inertia. We calculate these effective moments of inertia in this article, instantaneous deflection, this part A that I mentioned before. And for RC, there are two values listed here, IEDL, that's based on the dead loads, which are the sustained loads. So we calculate the effective moment of inertia for that model, stage 1 model. And then IE is the effective moment of inertia, the final one due to all loads is for the stage 3, is for the stage 3 model. So they are here. Then once we have the deflections, we check them against the limits. It's done here, criteria for deflection. Like if you remember this number, 0.426 and the 0.6, this showed up in this table, 0.4, 0.6. Now I will show it again. Now that moment of inertia that I mentioned, the 41,000, it came from here, from this moment of inertia due to all loads, because this is for stage 3. These are the deflections due to live load. So we needed the moment of inertia due to all loads. So again, then we list these deflections here in spec check results, the 0.4 that I mentioned before, 0.6, and then we calculate the ratio. So these are the instantaneous deflections due to live loads. Now I'm comparing here these deflections, the 0.4 here, with the 0.12, which we would get if we used either BrDR 7.5 or even BrDR 7.6, but with LRFD 9. We can see that there is a large increase, like about 3 times, even more than that. And that increase is because our moment of inertia, our stiffness, changed in the model so much. And since it's a simple span model with constant cross-section, this ratio of deflections is just the same as the ratio of the gross moment of inertia to the effective moment of inertia. Now, now I'm showing how time-dependent deflections are calculated. So there is this factor 2.0, the lambda delta factor, that's calculated in the time-dependent deflections, the B part of that article that changed. So we get 2.0, this will be the multiplier. Then we need the instantaneous deflections due to dead loads. They are in the stage 1 model for deflections. There are 3 load cases there. When we sum up these 3 numbers, they will add up to the points, to this 0.6. Then we have the 2.0, which is the factor, lambda D factor. We multiply it, we get 1.2. And then if we add that 1.2 with 0.6, that's the total time-dependent deflection that's listed here also in the spec check results file. The same process, we follow similar process for pre-stressed structures. There is just a few differences that I'm showing here. First, we don't consider, as I mentioned before, time-dependent deflections for pre-stress because LRFD, the factor lambda D factor just does not apply to pre-stress. And again, we do consider pre-stress these deflections in pre-stress design tool just on a different factor. Then for pre-stress, we list 3 stages rather than the final stage for as we do for RC. So we list that article where the effective moment of inertia is calculated separately for each stage. So you'll see this article in each stage. And also for pre-stress, the finite element analysis based on effective moment of inertia may not kick in if the tensile stresses are not high enough. We do check that condition. You would see it in the engine output window. And if that condition is satisfied, then we don't need to do second analysis. We just can base all the instantaneous deflections on the first analysis. So these are the differences for pre-stress. And then I'm just summarizing here that changes that AASHTO LRFD 10th edition introduced, the changes in formulas, and then we implemented these formulas and the changes basically from scratch because we did not use I effective or the lambda factor previously. So that covers the first topic. I'm moving on to the second topic now.
And I'm sorry, Daniel, I'll just pause real quick. I'm going to open up the second poll question.
I was about to say that, yes.
No problem.
Second poll, yes.
I'm going to open and launch up the second poll question. And we'll give everyone a few minutes and then we'll move on to the next one. Thank you all for participating in the poll. All right, I'm going to get to about 85% participation. Okay, awesome. So it looks like we have about what we expected, about 56% of you all from DOTs and 41 are industry consultants. And then we have a few local government folks. So thank you all for participating in the poll. Daniel, go ahead, you have the floor. Thank you.
Thank you. So for development length, we're not really starting from scratch. We of course had that all implemented in previous versions. It's just that AASHTO LRFD introduced quite a lot of changes. I'm summarizing them here. So the formula for LD development length and the basic development length, LDB, they changed. There are also changes in how the modification factors are applied. So we implemented that. Then there have been provisions added for the headed bars, and there is a new bar type that dual coated zinc and epoxy coated bars. So we also added that. And AASHTO LRFD 10th edition extended applicability of these formulas beyond bar 11, which was before. Now these formulas also apply to bar 14, size 14 and 18. And again, I'm showing on the left-hand side LRFD 9th, on the right-hand side LRFD 10th. The formulas changed. Like the biggest change is that there is just one formula now that covers straight bars and bars with hooks. There was no formula for headed bars, but now we can use that formula for headed bars too. And the way it's handled is there is this FH, which is the force developed either by hooked bars or by headed bars. And AASHTO LRFD gives us now the formulas how to calculate that, and then we plug it into the one new formula, and that gives us the basic development length. And then from that we can get the development length, and then we have the factors. So I will not go into all of these details, but I can show that we implemented some UI changes that were required. So right now, we can also specify that the bar is epoxy and zinc dual coated. And then we can also say that the bar has a head at start and at the end. Like the hooked bars were already there, but I'll just say that we cannot have a bar that's headed and hooked at the same time. Now that input for headed bars can show up in different places depending on the structure type. For RC, that's where it shows up on bar mark definitions, but for other structure types or substructure, it will be an input in a different place, but it will also have, say, head at start or head at the end. Also, we already had the calculations implemented, and they were shown again under engine output in this log file. And so the file was already there. We just modified it so that it shows for the bars that are not like fully developed, we show the calculation of the development length. And here I'm just showing how this file changed for the 9th edition on the left-hand side. This output looks slightly different, and then for the 10th edition, slightly different and slightly different values. I can just see that the values increased. I can say in all cases, but in this case, it increased by about 0.5 foot, which is 6 inches. And that covered the development length changes. And then again, after the LRFD changed, we implemented these changes to reflect them. It's just, we did not have to start from scratch. We had the implementation already in, and we just updated it to include the LRFD changes. And that concludes my part of the presentation. We move on now to steel. I'll turn it over to Ben. And this is time for the third poll.
All right, good morning. Daniel, I started sharing my screen, so I think you can stop sharing yours. And this will be the next poll question.
My apologies, 1 second. Let me launch the poll question. And this is the next, let's see. Okay, I'll ask the next poll question here.
Okay, has everyone had a chance to answer that poll question?
Yeah, we've got about 70% participating, so I think you can continue on.
Okay, sounds good. The next topic we will go over is going to be steel cross-frame stability checks and axial rigidity coefficient. The 10th edition spec update introduces new requirements for evaluating cross-frame and diaphragm members in steel girder bridges. This includes the stability checks and a coefficient for modeling specific cross-frame members. These new requirements for cross-frames are the result of two ballot items. A 2021 item introduced the new stability article, which is 67422, and provided a revision for 46344 or 334 to consider a stiffness reduction coefficient. And then in 2023, there's a modification to reduce the required strength and stiffness for cross frames when certain conditions are satisfied. For the stiffness requirement, the actual bracing torsional stiffness has to be greater than the required torsional stiffness. Beta T actual has to be greater than or equal to beta T required. The new article has detailed calculations and commentary to help compute actual and required stiffnesses. To take advantage of that lower stiffness in that 2023 update, 3 conditions have to be met. Cross frame is going to have to be at least 0.8 times the girder depth. It has to be attached to a full depth connection plate, and then that connection plate is going to have to be positively attached to both girder flanges. You'll see those three conditions show up throughout the new spec article and kind of referenced throughout these slides as well. The actual stiffness is going to be the sum of three different components. The bracing stiffness, beta BR, cross-section stiffness, beta SEC, and then a girder stiffness, beta G. And they're summed kind of like springs in series shown there. There's equations provided in the spec for each one of those components. I'll note for the cross-section distortion stiffness, if you do satisfy those three requirements with your diaphragm or cross frame, that'll be taken as infinity. So essentially that term will drop out of the equation. The required stiffness equations are shown on the right. It depends on MU over CB. MU is going to be moment from the girder itself. And when we evaluate these equations, we take CB equal to 1. The bracing strength requirements are essentially an extension of the stiffness requirements. From structural analysis, we have the equation relating force to stiffness times displacement. And so here, that stiffness requirement is multiplied by an assumed initial twist imperfection, which is LB over 500 H0, to arrive at these required bracing moments. The commentary to this new spec article is extensive. It provides detailed examples for how to distribute this required bracing moment into cross-frame member forces. And then whatever forces are calculated here are added to any forces calculated during the analysis. So the following conditions and analysis settings are required to evaluate these new stability requirements in AASHTO BrDR. It's going to only apply when you're running the 10th edition spec. Previous versions, this doesn't exist. It's a design check, so you'll need to use the LRFD designer view and a 3D finite element analysis. And so this is because it's a diaphragm spec check requirement, and spec checking for diaphragms occurs for 3D analysis only in BrDR. You'll need to enable spec checking for at least some of the diaphragms. You need to include girders in the analysis. So you'll mark girders as existing. And that's because we need those girder moments to compute the stability requirements. Additionally, connection plates, so transverse stiffeners, need to be provided at all diaphragm connection points. And that's to compute some of the stiffness calculations for connection plate geometry. And then that language about the connection plates being positively attached to both flanges, to indicate that in BrDR, you will need to define weld details for the transverse stiffener definition on both the top and bottom flange. There's also a new checkbox in the diaphragm definitions window saying tension only diagonal system. You use this to indicate how BrDR should distribute the bracing required moment, the MBR, to the cross-frame members. The checkbox will not impact the finite element model, only how those required bracing strength moments are distributed to the cross-frame members. Evaluation of the bracing stability requirements is performed in 2 steps. First is going to be determination of the strength and stiffness requirements, and then second is a comparison with the actual bracing strength and actual stiffness. These requirements, the strength and stiffness requirements, are computed after determining the girder member actions, but prior to final spec checking, because we need those girder member actions to determine the strength requirements, but we also need these strength requirements in order to evaluate the cross-frame member design ratios. So the determination of these requirements is going to be shown in the stability bracing force report. This is a text report available in the engine outputs. It will summarize the requirements and also provide detailed calculations for each cross frame and diaphragm. And it's laid out similar to how the spec article output will be laid out. When it comes to spec checking, the spec article 67422 will show up under a new folder in the spec check output tree. It's called brace system. And this is because these articles apply to the system as a whole, not the individual cross frame members. It's under the stage 1 folder. And the calculations are split into 2 articles, stiffness and strength. Stiffness will evaluate design ratio, comparing that actual required stiffness to the required bracing torsional stiffness. The strength article itself is just a calculation article showing how that NBR is distributed to cross-frame member forces. Those cross-frame member forces will then be evaluated using the standard, axial compression design ratio articles that you would normally see for those members. And they'll be added to any actions from the FE analysis. The axial rigidity of single angle and flange connected T cross frame members is generally going to be reduced due to the end connection eccentricities. This is implemented in BrDR within a reduced area in the finite element model. And we went with the reduced area since this coefficient applies specifically to the axial rigidity. And this way, the flexural rigidity of these members will be unaffected. Whenever this table of values is left blank, the coefficients will be computed according to the AASHTO specs, which is 0.65 AE for the non-composite model and 0.75 AE for the composite model. I'll note here, we have technical note 86. It's specifically related to these coefficients. Whenever they're left blank, the AASHTO engine running with the 10th edition specs will compute a coefficient. There may be existing models out there where someone has overridden some of the member properties to account for this reduced stiffness. Effectively, this would apply that reduction twice. So for any existing models out there where the member properties may have been overridden, we'd recommend reviewing them and either using an override coefficient in this table of 1.0 to not apply it a second time, or to update those member properties and then let the analysis engine determine the appropriate coefficient. And before we get into the LTB resistance, I think we have the last poll question.
I just launched the last poll question as the short answer. If you would not mind letting us know what you'd like to see at future webinars. And being that this is short answer, I'll let it get up to maybe halfway, and then you can continue on.
Okay.
All right. Okay, yep, you can go ahead and continue, and attendees, if you don't mind just answering that question as we go.
Okay, as many of you are aware, there are substantial changes to how lateral torsional buckling resistance is determined with the 10th edition spec update. And this really applies broadly to all of section 6.10 of the spec, but these are the specific articles for stress and moment resistance calculations. So the 2022 COBS ballot item 30 introduced these changes. Article 610.823 is the lateral torsional buckling resistance for stress. A633 is for moment. It adds a new spec article, D6.6, which is the calculation of the elastic lateral torsional buckling load ratio, referred to as gamma E. 6.3 changed several definitions and notations related to lateral torsional buckling. And then 610.16 revised definition of where lateral torsional buckling resistance should be computed. Steel members are often non-prismatic within the negative regions near piers due to flange transitions, and then also under the non-composite condition during construction. The goal of the spec update is to more accurately estimate the LTB resistance of these sections. This change also includes several other changes to the calculation, most notably the moment gradient modifier equation is replaced with a CB equation from the AISC specification using quarter point moments. The equation for the compact umbrace length limit, LP, also changes to an equation from the AISC specification. And then the compression flange stress at onset of nominal yielding, FYR, also changed. There, the coefficient used to often be taken as 0.7 times FYC. Now, in many cases, is 0.5 FYC. So there's a little bit of a reduction in FYR. For the anticipated effect of these changes, you may see an increase in the structural capacity of negative moment regions with non-prismatic umbrace lengths, or at least a more accurate estimation of that capacity. Due to that change in coefficient for FYR, there can be a reduction in capacity when comparing the 10th versus the 9th edition. Just make a note of that. The calculation location for LTB resistance has changed. Previously, the resistance would have been taken as the minimum within the umbrace length, meaning we calculated the resistance at every point and then found the minimum. Now that resistance is computed at a single location, which is defined as the location where FBU over RB, RH, FYC is maximum. So you'll now only see LTB resistance computed at a single point within each umbrace length. The new moment gradient modifier equation requires moments at the quarter points within the umbrace length. And so consequently, these points have been added to the FE model. So you might see a lot more nodes in the finite element model when comparing the 10th edition versus the 9th edition specs. And then the way that this CB equation is defined in the AASHTO specs, the quarter point moments, MA, MB, and MC, may be taken as 0 under some circumstances based on your flexure and then whether the top flange is continuously laterally braced. This can lead to a calculation of a CB factor as high as 5. So you might see that, especially near contraflexure regions, you can see larger CBs than what you are used to. And then the spec update also introduces methods for calculating the non-prismatic LTB resistance. This is accounted for with the new gamma E factor. We have several control options for steel members related to lateral torsional buckling. Consider concurrent moments in CB calculation. We'll use the quarter point moments corresponding to MU to compute CB. Typically, this will compute a larger C sub B factor. The compact web alternate equation refers to equation C F15 from the AISC commentary. There's several conditions to use this equation. Generally, it's going to apply for stringer members and floor system bridges. And then the new Appendix D 6.6 article introduces 3 methods for calculating gamma E. Method A, Method B, and Method C. That's how they call them. And Method A is going to be based on the AISC Design Guide 25, uses a modification factor. Method B uses weighted average cross-section. Method C is not implemented in BrDR. For Method B, for most inputs in BrDR are going to be compatible with both Method A and Method B. However, for some cross-section variations, the variation is going to be incompatible with the interpolation equations provided in Method B. And in that case, the program will revert to Method A if you have Method B selected. So the following example illustrates how to navigate the BrDR spec output for the new calculations. This is an umbrace length on the left side of an interior support locations. Within the FE model, nodes will be added at the brace points, at the quarter points, which are here indicated A, B, and C, and then at cross-section changes, here there's a flange transition between points A and B. And then the maximum moment in this case is on the right-hand side of this umbrace length at the support. Umbrace length calculation spec article includes a table showing all the user inputs which provide support to one or both flanges. And this is where that umbrace length is determined for the member. The LTB resistance is computed at the location where FBU over RBRH FYC is maximum, which in this case is that right-hand side of the umbrace length of the support location. So all other points for this article will just have a note saying the governing cross-section is, in this case, 140 foot left, pointing you where to look for the LTB resistance calculation. And then the LTB parameters, which are defined as RT, FE, and CB, are going to be computed in 610.823B for prismatic umbrace lengths, 610.823C for non-prismatic umbrace lengths. So depending on your flexure type and the umbrace length being prismatic or non-prismatic, that would be where you'd look for those parameters. These are the prismatic parameters. These are going to be similar to the 9th edition calcs, except CB as previously discussed. For non-prismatic umbrace lengths, all of these parameters are a function of gamma E. And then to figure out how gamma E is computed, you'd review the output from Appendix D 6.6, which will have articles based on Method A or Method B, depending on what you have selected. And this is just a brief calculation example running through some numbers to compare the two calculations side by side. It's a 2-span composite plate girder with constant web depth. However, it does have a non-prismatic umbrace length on the left side of the pier location. So for computing gamma E, obviously the 9th edition doesn't have any calculation. For the 10th edition, gamma E is computed using CBA, which does capture that moment gradient. And then it'll compute some elastic moments, ME1, at various points within the umbrace length. Chi is a non-prismatic geometry factor. All of this together, you'll compute gamma E. For the radius of gyration, the equation is going to be completely different between the 9th and 10th edition. The 10th edition is going to be a function of that gamma E factor. For LP, the coefficient has changed from 1.0 to 1.1. For FYR, the coefficient changed from 0.7 to 0.5, which does give a significant reduction in that FYR stress. And that carries through to differences in the computed LR as well. So then plugging in all those numbers and comparing the capacities, in the 9th edition for this unbraced length, we would get a capacity of 43.7 KSI. And with the 10th edition, we compute a capacity of 43.78 KSI. So after all that difference in calculation, end result is fairly similar. I'll make one final note here. There is a non-prismatic steel girder design guide expected to be published sometime next year. It has numerous detailed examples for how to compute the LTB resistance using each of method A, method B, and method C. It will be a great resource once that is available. So thank you. I think there's one final slide here from AASHTO for a discount on the 10th edition specs.
Thank you. And we have, I have that last poll question up still. If you all don't mind going back and letting us know what topics you'd like to see at future webinars, I'll leave that open until the webinar is closed. I don't currently see any open questions, but please feel free to add any questions into the Q&A portion. And the ProMiles team will answer it live or is going through and answering via text. And okay, is there anything else? Benjamin, Daniel?
Not from me, no.
Not from you all. Okay, wonderful. Well, let me come back on. All right, well, thank you all for attending our webinar. As we mentioned, we will send a recording of the webinar. I apologize for those of you who had some trouble hearing in the beginning. My suggestion would be turning the volume on your computer all the way up, just in case it is a little low at the beginning. Again, you can email me at hvon or any of the ProMiles staff with any questions, and we will send you the slides as well as the recording.
Hey, Hannah, there was a question about supporting galvanized rebar. I think I responded saying we do not support galvanized currently, but we do allow galvanized option in the UI, just as a clarification. It was on one of the chat. So just in the Q&A. So just clarifying that.
Great, thank you. And I think I see all the other questions have been answered about development length calculations. I suppose I assume that everyone should be able to see the answered questions in the Q&A portion. I can include the questions and the answers in our follow-up email if that's helpful for everyone, maybe just with those questions that ProMiles has answered. All right, well, wonderful. Thank you all for attending our webinar. I'm going to go ahead and end poll question 4, but feel free to email us any other suggested topics that you might have. And thank you all for joining. Have a wonderful rest of your Tuesday.